We're used to thinking of space as the emptiness in which things happen, like an empty warehouse ready to be filled, or a theater stage on which the events of the universe play out. But general relativity predicts that space is not just emptiness, it's a physical, dynamical thing. And that prediction has been borne out by many, many experiments. Space can bend because of matter and energy, curving the paths of objects that move inside of it. It can ripple with gravitational waves. And it can expand, creating more and more space in space. All of these seemingly different phenomena can be described by one idea: curvature of space, or space-time. In flat regions of space, like if there's no energy or matter nearby, objects traveling along parallel paths stay along parallel paths. In positively curved regions of space, like near planets or black holes, parallel paths converge, and in negatively curved regions of space, parallel paths, or even paths pointed at each other, diverge. But what about space as a whole? If space is positively curved everywhere, then there's only one shape space can be: a giant hyperspace potato. If you went in one direction for long enough, eventually you'd end up in the same place you started. If space is flat everywhere, its shape could be simple, just extend out straight to infinity. Or it could loop around in a periodic way, like in some video games. And if space is negatively curved everywhere, sports would be impossible. So which is it? There are basically two ways to measure the large-scale curvature of the universe. One is to measure the angles inside of triangles. If space is flat, the angles will add up to 180 degrees. But if space is curved, those angles will add up to more or less than 180 degrees, depending on the type of curvature. Cosmologists have done the equivalent of measuring our universe's triangles by looking at a picture of the early universe and studying the spatial relationship between different points on that picture. The second way to measure curvature is to measure the thing that causes space to curve in the first place: the density of energy and matter throughout the universe, which cosmologists have also measured. It turns out that in both cases, measurements show the universe to be pretty much flat, with a 0.4% margin of error. But before you get disappointed that we don't live in a cool cosmic hyper-potato, let me tell you one big problem. The fact that we live in a flat universe appears to be a gigantic, cosmic-level coincidence. If the universe had just a little bit more mass and energy, space would have curved one way, and if it had just a little bit less mass and energy, space would have curved the other way. But we seem to have just the right amount to make space perfectly flat, as far as we can tell. This perfect amount is the equivalent of 5 hydrogen atoms per cubic meter of space, on average. Those big empty parts of space make up for all the atoms we have crammed in here around us. If instead there were 6 hydrogen atoms per cubic meter of space on average, or 4, the entire universe would have been a lot more curved, or a lot less. And we so far have no idea why our universe has the mass energy density it does. When it comes to the curvature of the universe, our knowledge falls flat. Hey, this is Henry. As you may have noticed, this video was a collaboration with my friend Jorge Cham, who does PhD comics, and Daniel Weitzen, and they have a new book out called We Have No Idea. This video is based off a chapter in it, and there are plenty of other chapters about other things, like what is time, what is dark matter, dark energy, kind of the limits of our knowledge in physics and science in general. If you want to get a copy of We Have No Idea yourself, you just go to wehavenoidea.com, and you can find out different ways of buying it there.